he's like, no, he's like, act like a complete geek. Like, it sounds yeah, but I read 5 PPD and it's hard, and he'll get frustrated. He'll just do it.
I want him to do it for me though, I want him to explain.
Well, no, he'll explain it to you, but he'll also do it, and then he'll explain it for the entire class. Because if he thinks you don't have it, he thinks nobody else will.
The other day, like,
No, I'm talking about model class.
he was trying to do something. The other day, he was trying to do something and then he didn't do it. Like, it took him like 45 minutes to class to like get the what he wanted to go. Dude, next one.
Hey, I'm going to start class a little early. I'm already recording, but I'm not going to cover any material. I'm going to just talk about the exam I just handed to you. So if you're here a little early, you get a little bonus information. First of all, there is a typo on it. It's actually due Wednesday, not Monday.
Because you love us, right?
Well, the date's correct. And, but it's not, it says Monday there. So that's next Wednesday. All of these problems should be done using concepts from chapter 10. We're actually starting chapter 11 today. So remember I said there's going to be a little bit of a lag? Okay, so you should have all the homework done for these sections, so you should be able to handle this whole thing theoretically. Like you could start it today. So let's talk about this first one. By the way, online in Canvas I have under Files, and then I think in there it's under something like Mini Exams. Then there's both the PDF version of this and then what's called the CDF version. Does anyone know what the CDF version is?
The one you use in class?
I use what is the extension on NB? So it's .pdf, .cdf, .nb. NB stands for notebook, and this is Mathematica's file type. If I save the file as a CDF, then you can go to wolfram.com and you can download what they call their free CDF player. And then what that allows you to do is open this file, and then you can like move things around, and everything I do in class you can do, except you can't put your code, like you can't change the code. You can't edit the actual code that I made. You can't make your own program. So you can just view someone else's work. All right? So that actually might be helpful in this one. I don't know, because they're, like for number 1, find the equation of the plane containing the point of intersection of the lines R1 and R2, which is also parallel to the plane, blah, blah, blah. So you see how it looks like that second plane, 2x minus 4y plus 6z equals 12. Notice it's like a lighter color. Well, if you actually open up the CDF player, both the lines and the plane are different colors. And then when there's an image, there's a picture that goes with this, and you can see like if it's a blue, like if R1 is blue, then the line on in the image will be blue. So it's like color coded or color matched. So on number 1, find the equation of the plane. What do you need for the equation of a plane? A point and we didn't call it the direction vector. It was something else. That's for the line. You're thinking maybe line. You do need a point though, right?
Oh, normal vector.
Normal vector. You need the normal vector of the plane, right? That's all you need to come up with the equation of a plane. A point and a normal vector. Now you could also get 3 points, and you could get the equation of a plane, but point and normal vector. So do you want to talk a little bit more about that one? Number 1, find the equation of the plane containing the point of intersection of 2 lines. So you have R1 and R2, right? You have 2 lines. I started early just to talk about the test, okay? You have 2 lines, R1 and R2. They hit each other at a point, don't they? Well, that's what it says, right? Find the equation of the plane containing the point of intersection of these lines. So remember we just said you have to have a point and a normal vector, right?
Yeah.
That's the point. The question is, how do you find the intersection of two lines? Well, you have to find a point, x, y, z, that satisfies both of these simultaneously, right? Yeah, you're going to have to do something, right? Okay, but that's your point that I'm talking about. But then listen to this. Which is also parallel to this plane. So the plane you're looking for goes through this point, but is parallel to some other plane. You already have the point, you just need the normal vector, right? So how is that information going to help you get the normal vector? Can anyone tell me right now? The coefficients of this plane right here? Those are the normal, that's the normal vector of this plane, right? That's parallel. How does that help you? Yeah, if you're parallel to that plane, think about two planes, right? If these two planes are parallel, what do they have in common? What can you tell me about their normal vectors? You can use the same one. They both have the same normal vectors, right? So really this problem comes down to finding this point, because once you have the point, you just need the normal vector. Since it's parallel, you can just use that other plane's normal vector. That's a big hint, but you understand? Okay, number 2. Find the equation of a line through a point. Okay, so what do you need to find the equation of a line? A direction vector and a point, right? And I'm already giving you, find the equation of the line through a point. You see that? You already have a point. All you need now is the direction vector of the line. But here's the catch. You got to figure out what the hell to do with this. Okay, this line is both parallel to a certain plane and perpendicular to some other line. Okay, so you're looking for a line, right, that's sitting out here in space that is parallel to some plane. So let's say this is the plane. Your line has to be parallel to this plane, right? There are an infinite number of lines that are parallel, aren't there? Look at all these. I'm spinning this around, but all these lines are parallel to that plane, aren't they? So it can be any of these. But you also have that you must be perpendicular to some other line. So that means that, that plane sitting here, don't forget that plane. We have to be one of these, right? But there's some other line sitting somewhere that you have to be perpendicular to. So you've got to rotate this to the right place to make these two perpendicular. You'll have to think about that. Remember though, all you need to do in that problem really is to find that direction vector. That's all you need. 3, shortest distance problem. I did in class how to find the shortest distance between two planes, and I did how to find the shortest distance between a point and a line. Right? I did those two.
Is that the comp UV?
Yeah, I had to do with that. There's 2 different formulas. One of them had a dot product, the other one had the component of some vector on the other. Okay, so in class I taught you how to go find the shortest distance from a point to a plane, and then also a point to a line, right? So number 3 is saying find the shortest distance from the center of this quadratic surface. So that means you've got some quadratic surface setting out there. Could be a lot of different things. You've got to figure out what the center of that is. Okay, so I'm just going to act like it's an ellipse. So let's say ellipsoid. Sorry, you have a 3-dimensional ellipsoid, and there's its center, right? You're trying to find the shortest distance between the center of that and the line of intersection of 2 planes. So you've got a plane over here, you got another plane over here, and they hit each other in a line, don't they? So you've got to figure out what that point is, you've got to figure out what this line is, and then once you do that, you can do what I did in class, shortest distance between a point and a line. Understand? Number 4, that's just going to test your ability to take some limits. And I'll just warn you, you need L'Hopital's rule. And number 5, I think you can mess with 5 yourself. All right.
Question.
Yes.
It says due Monday 10/4.
Yeah, I said it's Wednesday.
Okay.
Yeah, it's Wednesday. That was a typo. So everyone have a copy of that now? Yes? If you're just coming in, the take-home test is there. There's a typo. It's due Wednesday, not Monday, October 4th.
Can we work together on this?
Yes, there's still no restrictions I'm putting on that. You're allowed to work together. Just again, make sure you state when you turn it in who you worked with. All right, let's get going. Hope everyone had a good weekend. We got a lot to do. All right, so we are going to start chapter 11 today. And the title of chapter 11 is Partial Derivatives. That's the chapter title. But there's a lot in here other than partial derivatives. All right, so functions of several variables. That's the first section. So a function of two variables. We have seen that equations involving x, y, and z give us surfaces, right? We did that in section 10.7, I believe, or 10.6, where we had spheres and we had hyperboloids and ellipsoids. Anytime we had three variables in an equation, it gave us a surface. If it is possible, all right, this is a big if it is possible to solve or isolate z in that equation, then z can be seen as a function of both x and y. And we can write it this way. So we've been used to doing this in the past. If somebody gave you an equation like 3x plus y equals 4, we could solve this for y and get y equals negative 3x plus 4. And then we could say, oh, this y is a function of x. And we would say, well, that's a line, right? You give me x, it's going to spit out y. We can do the same kind of thing here. If we can isolate that z variable, then we can say that z depends on two things. You give me an x and a y, and I will be able to produce the z value. Note also that to be a function, there still needs to be one input, one output. So when we use the word function, we have to pay attention to that. You cannot have one input that goes to two different places. So we still almost kind of have like a vertical line test here, but it's going to be a little different. Visually, it'll look different. All right, let me try and make this a little bit bigger. All right, with this notation, it is important to see that the domain of this function are all the ordered pairs x, y, which can be plugged into the function. This means that our domain is two-dimensional. So if you look back again, let's take an example of something that we've seen before. That is a root function, right? We studied that in college algebra. This has some domain restrictions, doesn't it? The domain restrictions here are that x has to be greater than or equal to 0. Now visually, I don't think you've ever looked at it this way, but if we look at the input and the output of this function, the input is a single number, isn't it? And the output is a single number. So the input I could look at as a number line. That's one-dimensional, right? A line has one dimension to it. This has one dimension. So the input here is, let's see, 0 and out. I can plug in anything here, right? And then it spits it out over here. You plug in 0 specifically, it's going to spit out 0, right? If you plug in 1, it's going to spit out 1. If you plug in 2, it's going to spit out 4, right? That's the idea of what's happening. But we never did it this way, right? We always did this. We said, here's the input. And here, root 2. Sorry. I was thinking x squared. I don't know why I was thinking x squared. Let's change this. This will be root 2. Pardon me. When we look at it, though, normally we graph it, don't we? We use 2 dimensions, and this is the graph of it. Agreed? Now, what I want you to realize here is that when we visualize this function, this axis is our input, this axis is our output, right? So we need 2 dimensions to visualize this function. Understand? What I'm saying in this note is that the domain of a function of x and y requires 2 dimensions for the input, because you have to put in ordered pairs. And then it spits out a single number, doesn't it? So it looks more like this. If I were to do something similar to this, I would have, let's take z equals some function of x and y. And I haven't given you an example yet, but I'll give you a very simple example, x plus y. Then if I'm trying to visualize the input and the output separately, my input requires 2 dimensions. My output requires 1 dimension, right? Like this. So what would happen to this point right here, 0, 0? Where would that go?
0.
You plug in 0 for x, 0 for y, it would spit it out over here as 0, right? So that point would go here. Where would the point, let's say, this point right here, 1, 1. How about that point right there, 1, 1? Where would that go? So you're going to go 1 and 1 here, so that would, what, come out to 2? So that point gets mapped here, right? Do y'all see what I'm kind of doing here? Can you give me an example of a point that would also go to 0, but not this one, not 0, 0? 1, negative 1? 1, negative 1, this point right here. That point would also go to 0. Now, is that okay? Is this still a function? Yes, it's a function, because to be a function, each one of these has to go to one place. It's okay if 2 different inputs go to the same output. It's not okay to have one input go to 2 outputs. So we can't have this go to 2 different numbers. Understand? Now, this is a very difficult way of visualizing it. So what we try and do is visualize it like we did with the square root function. We try and put it all into one picture. So do you see that we're going to have to somehow in our picture have 2 dimensions for our input and 1 for the out? Right? So we need a total of 3. So why don't we do this? X, Y, that's our domain is the ground now, isn't it? And our output is going to be the height at that point. So if I were to take this 0, 0, that would be right here, wouldn't it? And it's going to spit out how high? 0, so it's going to be right there at the origin. If I go out to, let's say, 1, 1, which would be kind of like this point right here, where's that going to go to? 2, so I go up 2 units, right? Like that. So you've got a height of 2 units. Understand? How about this one right here? 1, negative 1.
Why does like axis like 1 though?
Pardon? What's the question? Are you talking right hand or no? We're okay? So if I go 1, negative 1, that's right here. Y'all see that on the ground? And where does that go to? 0, so it should just be right there on the ground. You get the idea? 2 inputs, right? 2-dimensional space for the input. The output is a real number. So if you go on and do more math, like I'm talking for people who are more like math majors, this function right here is a function that we would say goes from R to R. It goes from a real number to a real number, okay? This function right here, we say goes from R2 to R. Not R2, R2 to R. See, 2-dimensional space to 1-dimensional space. It is possible to have functions that go from 2-dimensional to 2-dimensional. It is possible. We're not going to study them, all right? Well, yeah, we're not. R2 to R2, that is possible. I mean, I'll make one up right now. F of x, y, it takes in 2, right? Equals, and it's going to spit out right now an ordered pair. X squared y, comma, x plus y. I just made up a function that does 2 to 2. Yes?
Do these functions have parent functions do they have parent functions?
Like the square root of x is kind of like this basic function. Nah. I guess you could. But not like it was in algebra. It's not like, okay, you've got the root function, you got the identity, it's not like that. Does anybody see, I'm showing this one to you for a reason. Do you see that it's an input, 2-dimensional input? Do you see that the output's 2-dimensional? Okay, do you see where I would run into a problem right here if we tried to visualize it?
We'd have to,
How are you going to do that?
We have one input for two outputs.
Well, but your input, to visualize the input, you're going to need to have something that goes from R2, right? And that's the input, and the output goes to R2 also, right? Like for example, if I plug in 0, 0, it's going to spit out 0, 0, isn't it? So it's going to be right here. That one goes to here. But what if I plug in 1, 1? 1, 1. Where does that point go to? It goes to 1, 2. Right here. You see that? Understand? Now, see how we took these two and we put them together into a picture so we could see it? What about here? What happens when I try and put the input and output together into a picture? I need four-dimensional space. And I can't do that. Right? 1, 3.
You're taking the x, the variable. X.
I'm plugging in 1, 1.
Yeah, so it's
And it's
1,
going to 1 squared times 1, which is just 1. And it's going 1 plus 1, which is 2.
Yeah, and then you put it back into the function.
Oh, no, no, no. This is something different.
Oh, okay.
This is something different. Yeah, no. These are separate ideas here. This is totally separate.
Okay.
And this is separate. I'm just trying to get you to see that what we're doing today is we're trying to introduce the idea of a function that takes in two variables, spits out one. And that means we can work with it, we can visualize it because it's three-dimensional. However, we could very easily come up with a function that goes from R2 to R2, and then we won't be able to visualize it. And really, pardon?
Like, people who study these kind of functions, like, what's the point of studying them if you can't visualize the output?
Well, because there's many things in the real world that have, like, just think about predicting weather, right? How many variables they take in, right? Their temperature, pressure, humidity, all these different things are the input, and they put it through some algorithm that has an output, right? That output might be a number, that output might be several numbers, right? And so really there's no limit as to, you don't have to see it. To define a function, you don't have to be able to see it. It's just however you want to define it. Here's a good example. What if I want a function that takes in your position on the Earth and spits out the temperature? Okay? Then your input is going to need what? To figure out where you are on the Earth, you're going to need three inputs, right? Almost like an x, y, z to get a position. And then the output's going to be a number, the temperature. That's going to require 4 dimensions. So even though we can't see it, it's very, applicable, if that makes sense. So mathematicians study things like this, like, functions that go from Rn to Rm. There's no limit to it. And that's why there are actually some historically very brilliant mathematicians who are blind or visually impaired and, born blind. And then when they study things, and it's like, you'd think they would be at a disadvantage because we get to see, like, visualize things. But once you start doing things like this, the fact that visual people need to see it, the people who are visually impaired have an easier time with higher dimensional stuff like this because their whole perspective is totally different, if that makes sense. Okay. All right, but we're going to try and stick with functions we can see, at least for now, and then we will extend it a little bit later where we won't be able to see the things necessarily. What I promise you is that we will always be able to see the domain. Okay, the domain will always be visual, but the output may not. All right? All right, I went off on a little tangent there. I mean, we're still in here, but I talked a little bit more about that than I wanted to. All right, so we need three-dimensional space to see these things. And I'm going to show you these, all right? But let's just first practice algebraically, making sure we can manipulate and understand what's going on with this function. So if f of x, y equals the square root of x plus y plus 1 over x minus 3, then evaluate the following things. So let's first just plug in some numbers. What does f21 mean? That just means replace x with 2 and y with 1, right? So what would we get? Root 2 plus 1 plus 1, yep, over 2 minus 3. So we got root 4 over negative 1, which is negative 2. Agree? Okay. So if we were to plug in 2, 1, that ordered pair, it's going to spit out the value of negative 2. How about the next one, f of 0, 0? root 1, and then on the bottom, negative 3, so negative 1/3. So it spit out a negative fraction. Is this clear? I'm assuming y'all plugging in is not an issue here? Sure? Okay. How about f of negative 4, 1?
Negative 2.
Negative 4, 1. So on the top you get what, negative 4 plus 1 plus 1 over negative 4 minus 3. So, uh-oh. We have a problem here, don't we? Pardon me?
The top is imaginary? Like,
Yeah, so we have root negative 2 over negative 7. So when we have roots under negative numbers under roots, this is where in college algebra you talked about imaginary numbers. Did you do any imaginary numbers in Cal 1? Cal 2? No? Okay. What we're studying here is something you may or may not have been pointed out to you, but this entire book, Calculus 1, 2, and 3, are all calculus of a single real variable. That's what I was referring to. We are only dealing with real numbers here. We are not ever going to try and deal with imaginary numbers. If you want to do that, you take a class called complex variables. And that's where you start doing all the calculus that we've been doing with complex numbers. Here's the problem with it, though. Here's the problem. All right, and you're going to see it right away. Does anyone remember what a complex number looks like? I'm going to show you. A plus bi. That's what complex numbers look like. And if I were to try and say, hey, what's the complex number 3 plus I look like? Then you would actually have to go out 3 and go up 1, and that dot represents that imaginary number. Okay? If you haven't seen this or you don't remember, that's fine. But if I try and come up with a function, okay, that goes from a complex number to a complex number. So not from real to real. That's the way we do real to real. Not that, okay? But a function that goes from the complex numbers to the complex numbers, CC. If you try and do that, how many dimensions do you need for the input? How many do you need for the output? 2. How many do you need total? 4. It's too much for us to handle right now, all right? So that's why you have to wait till you finish the calculus sequence. Then you're mathematically mature enough, mentally able to start working with functions that you can't see, all right? It's very different. Look, I got to shut up. I got to get back to this. But this is fascinating stuff. There's something in here that's very subtle that you don't realize. If you take a real number, okay, if you give me 2 real numbers, here we go. They have something called trichotomy. And it seems like no big deal, but it is a huge deal. And that's if you give me 2 real numbers, they're either one of them is bigger than the other, or they're the same number. Okay? So let's say we call this x1 and x2. I know one of these 3 things are true. That's why we call it trichotomy. x1 is either bigger than x2, x1 is either less than x2, or x1 is either equal to x2. Those are the only 3 possibilities if you give me 2 real numbers. Trichotomy. Complex numbers don't work that way. Because if you give me 2 complex numbers in a plane, you can't talk about which is bigger than the other. You can't. You don't have that natural order anymore, do you? So when you think about all these inequalities that you deal with in real analysis or real variables, this is bigger than this, or we need that to be smaller than that, it all goes away here. And so it becomes messy. It becomes extremely messy. So we separate imaginary numbers out of our calculus when we first introduce it. So this for us today is undefined. Okay? That's what this is going to be, undefined. We don't even care about the I, undefined. All right, so the answer to C is undefined. That means we can't plug that point in, right? This point, negative 4, 1, is not in the domain of the function, right? It's not in the domain. All right.
Can you explain C again?
C. Oh, you want to start? Let me start with square roots of negative numbers. Can I start there? Okay, so we've got C down. Let's talk about D. Determine the domain and sketch the domain in R2. This is something you will have to do on an in-class exam, all right? I probably won't ask you parts A, B, and C, but I'll most likely ask you to sketch the domain of a function of two variables. Yes?
Does that mean I can have like a, why is specifically in R2 like?
Remember the domain is in R2? The things we can plug in come from here and get spit out over here, right? I want to know what it looks like over here. I want you to sketch me what can go in, all right? All right, so let's try and sketch what can go in. It seems like this would be tough, but it's actually not that bad. Let's take a look at the problems that we have with this function. Can somebody tell me one issue that we have with this function?
Yeah, it's undefined at 3.
At what 3?
Positive 3.
At what's positive 3? We have two inputs, yeah. Okay, so we know this. X cannot be equal to 3, right? We know that so far?
Yes.
What does that look like in two-dimensional space? A dashed line at 3, what kind of line? Vertical? Okay, so 1, 2, 3, here's 3, right? So if we were to be talking about the domain of this function right now, right? That's what we're talking about, the domain? Right now, we're saying, look, everything can be there except your x can never be 3. And that means any point along this dashed line, right? Any point along there is going to have an x coordinate of 3. And that's going to cause a problem right here. What is that? I just got a draft of, is that Chinese food or something?
Yeah, that's fine.
Oh, it's your, okay. It smells good. God, it smells real good.
So for x plus y, is that how you will talk about the domain? X plus y cannot be.
Exactly. That's what I'm going to look at next. So imagine, let's do it this way. Let's start by saying, look, let's just say that right now we can plug anything in, right? And let's start taking things out. This line is out. Okay, so right now it's everything to the left, everything to the right is good. But there's one other condition that we must hold, and that's this entire expression cannot be negative, right? That can't be negative. So I'm going to write that down. I also need that x plus y plus 1. To say it can't be negative means it needs to be bigger than or equal to 0. That's what that means, right? I need the radicand, the thing under the radical, to maintain non-negative values. So that right there is something I did in my Math 1324 class last week. This is called a linear inequality. And so the way you do these is you first turn it into an equation. I'm going to put this here. Linear, if you need to go back and review this, linear inequality. That's what the topic is. So what we do to solve these is we first turn it into an equation. So we treat it like an equals. And then we look at it and we say, hey, that's a line. Remember? Oh, yeah, that looks like a line. If you solve it for y, it's y equals negative x plus 1. That's y equals mx plus b.
Wouldn't it be negative x?
Yeah, negative 1. Negative 1. Thank you. Right? That's just a line. Now, I can graph that line, can't I? Do you all remember, anyone, how to finish this off? Because I'm going to graph this line right now, but is that all I do? Just graph the line, I'm done? I have to shade, right? I have to shade like either above or below the line. Now, when I graph this line, am I going to graph this line as a solid line or a dashed line? This right here has an equals, right? And we are saying that it's okay for this to equal 0, right? Because you can take the square root of 0. Okay, so I want to include the line itself. That is valid. So let me try and graph this. I'm going to go to y equals negative 1, go to my y-intercept here, and then my slope is negative 1 over 1. So from here, just down 1 over 1. And I'm going to draw a solid line through these. Okay? And now I have to either shade everything below the line or above the line. Does anybody have a way of doing that? Why though? So you're testing a point, right? Okay, that's the technique you should do. I've heard some of my students last week were telling me, well, my teacher told me that if it was bigger than you did above or below. That is very dangerous, okay? What you need to do is just test a point. It's not going to take very long. let's just see, does this point right here satisfy that inequality? So let's try 0, 0. So just plug in 0, 0 plus 1 is 1 bigger than 0. Yes? It is, right? So since 1 is bigger than 0, this point is part of our answers. All right? If this had turned out to not be true, I would not need to test another point. I would just know, since this is not true, it's the other side of the line that I would shade. All right? So I'm ready to shade. My answer is everything over here, okay? Everything over here, like this. All of that, but imagine you have to take out this vertical line just until you get to here. So there's actually like a little hole here in this line also. You can't have that hole. I mean, you can't have that point because x would be 3 there, right? Even though it's on this line, it's a problem because x would be 3. So can you all see that? That's an infinite number of points. It's an entire region of two-dimensional space missing this piece in here. That's the domain. So when you try and plug something in over here, we know it's not going to work, right? That's how we get domains. Now, the range is much more difficult. Does anyone remember in algebra how you could find the range? No? I'll give you a hint, or I'll just tell you. How about that? To find the range of a function, what you could do in algebra was you could find its inverse function. Once you find its inverse function, you look at its domain. Okay? And that's the range of this, because the inverse, a function and its inverse, their domains and ranges swap places. The problem here is that finding an inverse for this is really not possible, because, I'm not going to say not possible, but it's not as easy because you have 3 variables. It was easy when there were 2, because if it was solve for y, to get the inverse, you just solve for x. Here, do you solve for x or y? It's a mess. So the range of this, we are going to just make this optional. We are actually, I just want you to consider the fact that it's hard. That's really what that whole thing is there for, is just to say, hey, the ranges of these things are difficult. I mean, we might be able to look at it and determine like a biggest value, but I don't think so. I don't think that there's like a highest value this could ever be. Like imagine you hold your x at 4, okay, everyone? X is 4. Then, do you agree the bottom is 1? Now just let your y get bigger and bigger and bigger. So I'm like, go out to 4 and pick any number along this line, stay above this, anything here. If I kept going up there and picking points, wouldn't this just start getting huge? Yeah. This thing would explode, wouldn't it? It would just get massively large. So it looks like it can become infinite. Can it ever be 0? Can you ever have that function be 0?
Yes.
How? You could plug in -1, 0. Right? -1, 0. Would that work? Should. Is -1, 0 here? It is. It's right there. So that would make it 0. So it looks like we can get 0 out. We can get all positive numbers out. How about negative numbers? Can we get all the negative numbers out?
As long as...
Yeah, why don't we make x2 now? Watch. If we make x2, now there'll be -1 on the bottom. If we hold x to be 2 here and let y get big again, you're going to have a bunch of huge negative numbers now. It appears, just by a visual, if you follow that logic, which I know not everyone's going to follow that logic, but if you did, it appears that the range of this is -infinity to infinity. Very difficult to check, though. All right? So understand we're kind of skipping range. I want you to just look at it, maybe think about it, but don't worry about being tested on it. I think it's time to look at these. What do these things look like, right? I told you that they were surfaces, right? All right, so this is kind of let's kind of back up and make sure we understand what's going on. We're going to choose points in two-dimensional space, plug them into a function, and it's going to spit out outputs, right? If we try and visualize that three-dimensionally, then the ground there the ground here is like the XY, and it's going to spit out points. So if I pick an XY, something down here, it spits out a Z value. So what I did is I'm using a specific example, and it's a bunch of points, right? That's all it is. There's a bunch of points down here. Each of these points on the XY plane get mapped to some Z value. And if I start doing like millions and millions of points, at some point I start to create something. And if we do all the points, if it was possible, then we would get some sort of surface, right? So it's not solid below here, okay? It's just the surface itself. So functions of two variables like this look like surfaces, sheets that are blowing in the wind, and then you take a snapshot, there it is. That's your surface. With me? Take that out of there. And then this is another visual representation of what's going on. Here I actually have the domain separated from the picture. So the ground here, the ground is actually this right here. So you can see the point I'm plugging in. It gets plugged in and it winds up somewhere on this surface. And if I move my point around, you can see it moving along that surface, right? Let me try and get it back over here. Get over here. See it coming up towards the front here? Okay, so every point here, every point on this surface corresponds to some input off this plane down here. So you ready to see that graph that we just did? This is the specific example. We just plugged in 3 points. We also, well, we tried to plug in 3. The first 2 gave us values. The third one was undefined. Then we found the domain, the range. We kind of waved our hands at a little bit. You ready to see it? Here it is. This is what it looks like.
Shouldn't it go to infinity?
It is going to infinity. Do you see my computer trying to freak out and like trying to figure out what's going on here? Do you see it? No? Doesn't look like it to you? Okay, maybe look at it from the side. This will be an interesting way of looking at it. Look at it from the side here. Do you see it going to infinity? You see the surface going like this? Taking off? Doesn't that look like an asymptote back from college algebra where you had that thing happening? Now the computer at some point I had to make it still fit it in here, and the computer at some point has to stop. It can't keep doing the surface, right? So is this, do you see our answer in here? So what I did is I made it so you can look at it just from straight down. If we look at it from straight down, shouldn't it kind of look like our answer? So there it is from above. Isn't that what we had? Wasn't it this line with this thing taken out? So that's it. That's your domain.
So the range was integrated into infinity?
Let me see. I think it is, because we can get 0 out, and I can create all the positives and all the negatives. I'm pretty sure it is. Pretty cool, huh?
That shows the domain and the range, but didn't the 2 points give us another number? So then that should be on this. Why is it flat?
Wait a minute. Say again.
The 2 points that you give us are X and Y. When we plug that in, that should give us a number.
Yes.
So why is that flat? Because isn't that number the Z coordinate?
What? Yes, it's there. Let me see. We plugged in. What point did we plug in? What was the first one we plugged in? 2, 1. So I think this is 2, 4, 6, 8, 10. So 2, 1 was right here, right? And what did it spit out? -2. So this might be hard to do here, but let me see. And it's going to be hard. It's hard to see. It's hard to see it. It's right in here. But see, look at my scale. My scale on my z-axis is going up 50. So it's hard to see -2 there.
So it's not really flat.
It looks flat. It's not. Oh yeah, it's definitely not flat. That's not the XY plane. You might be able to see a little bit of a taper to it. Let me spin it around. I don't know. You can see that it is curved, right? It is curved. Is that okay? In fact, here's the function, right? If you fix x to be, I'll do 4 again because it's convenient. If I fix x to be 4, doesn't this just really turn into this? Uh, 5 plus 1. Right? So if I just go to this function, I say, hey, look, I'm just always going to let x be 4, okay? Then that becomes 4 plus 1, that's 5. That becomes 4 minus 3, that's 1. So it just becomes this function, right? What type of function is this? That's a square root function. Good old classic square root function, which should look like this, shouldn't it? And that's exactly what we're seeing here. This curve right here, you know what? It's not that way. Hold on. I got to turn it the other way. Man, you can't see it. Oh, there it is. That's your root function. There's a bunch of them, because if I adjust x, if I make x a different one, it's going to move that root function back and forth. All right, we're getting a little beyond where we need to be right now. What I want you to see is how we found the domain algebraically, and it matches with the picture. Here's a new one. Why don't I give you a minute to do that? See if you can handle that domain. You don't have to really do the range. Anybody have a picture of the domain yet? Okay. Okay. squeeze right here real quick. Okay.
I didn't do it in just 4 wide.